This is a video abstract for the Journal of Number Theory paper, Newman's Conjecture in Function Fields, by Alan Chang, David Mehrle, Stephen J. Miller, Tomer Reiter, Joseph Stahl, and Dylan Yott. De Bruijn and Newman introduced a deformation of the completed Riemann zeta function and proved that there is a real constant lambda which encodes the movement of the non-trivial zeros of zeta under the deformation. The Riemann hypothesis is equivalent to the assertion that lambda is less than or equal to 0. Newman, however, conjectured that lambda is greater than or equal to 0, remarking, "The new conjecture is a quantitative version of the dictum that the Riemann hypothesis, if true, is only barely so." Andrade, Chang, and Miller extended the machinery developed by Newman to L functions for function fields. For each L function, there is an associated de Bruijn-Newman constant. In this setting, we must consider a modified Newman's conjecture. The supremum of de Bruijn-Newman constants over a family of L functions is greater than or equal to 0. We extend the results of Andrade, Chang, and Miller by proving this modified Newman's conjecture for several families of L functions. In contrast with previous work, we are able to exhibit specific L functions for which the de Bruijn-Newman constant is 0, and thereby prove a stronger statement. Instead of a supremum over a family of L functions, we find that a maximum over a family of L functions. Our main result is the fact that for f a family of L functions, q an odd prime power, we let d be the L function associated to the quadratic character modulo x to the q minus x. If the L function d is in this family f, then the modified Newman's conjecture holds. We prove this theorem using geometric techniques to show that a certain deformed L function must have a double root, which in turn implies that the associated de Bruijn-Newman constant is non-negative, thereby establishing this modified Newman's conjecture.